Okay, good afternoon. We can start perhaps. Today to welcome Professor Subhro Bhattacharjee from ICTS Bangalore as our Institute Colloquium speaker on the occasion of the Institute's 60 years anniversary. Just to introduce Subhro, so Subhro finished his undergrad at Presidency College in Calcutta, and after that joined ISC as the integrated PhD student, and there he finished his PhD around 2011. Yeah, so and then so he was formerly under the mentorship of Professor H.R. Krishnamurthy, but during his PhD days he was working with different people. He spent actually quite a lot of time here in math science working with Professor Bhaskaran and Professor Shankar, and also at the same time he was working, he spent quite a lot of time in Dresden working in the group of Professor Roderick Mosner. Then after finishing his PhD, Subhro went to Toronto to do his first postdoc in the group of Youngbeck Kim, and then moved again to Dresden to do his second stint in the group as a postdoc in the group of Professor Roderick Mosner. And after that he joined ICTS as faculty member in 2015 and has been there since then, and is of course doing some excellent work in different aspects of condensed matter. And today he'll be telling us about his new exciting findings in the context of jam granular solids. Subhro, over to you.
Okay, so thank you Pinaki and Shantan for inviting me, and also Pinaki for this kind introduction. And it's great to be back in math science, where as Pinaki pointed out, I spent some time during my PhD working on interesting things and learning a lot of things. So what I'll be talking about is something that we have been doing recently, and it's a part of this ongoing work. And I should start with a disclaimer that I can say something about the first two words, like the emergent electromagnetism. That's what I am more familiar with. But regarding jammed granular solids, I know close to nothing, and actually people like Pinaki are real experts. So I'll basically be able to say you everything I know about jammed solids in like 10 minutes, and then I'll be talking mostly about electromagnetism, and hopefully we'll see the connection that is sort of been of interest to me and a bunch of people that we are working together on this. Okay, so if I run out of time, so let me start with sort of pointing out the partners in crime, and particularly all these things started out with Bulbul Chakraborty and Kabir Ramola giving a set of talks at ICTS way back in 2017, pointing out some of the features of granular solids, and since then we have been working together, and these are the two people who did all the heavy lifting, Jishnu and Michael, and some of the experiments were done by these two people. And we have a couple of things already out, and I'll be mostly talking about these things. All the references, etc., you would find in these two papers, and these are the funding agencies that have helped us carry out this research. Okay, so this is literally all I know about granular material. So these are these sort of things like sand particles, or this collection of these grains of various kinds, which are roughly put together, and the question generally is that is it a solid or a liquid? So and it is a question that is not new. It has been sort of addressed in various ways over several decades, and the point is that depending upon how you deal with them, they appear as solids like the sand on the beach, or as a fluid like this sand clog that we no longer use very often, but there it flows. Okay, and more particularly the question that we can try and ask as physicists is that what are the statics and dynamics of such granular assemblies, and one point where it departs from regular things that statistical mechanics person I learned in my coursework is that unlike things like gas particles, etc., these grains which are involved, sand grains or whatever, they are so big that at ambient temperature, the Brownian motion of the grains or the thermal fluctuations are completely irrelevant. Okay, and or they are sort of much more secondary to the mechanical aspects of these assemblies, which I'll talk about. So for all practical purposes, one can think about them as zero temperature assemblies, and this is why these are called athermal assemblies. Okay, and this is one place where it starts immediately departing from the Gibbs type of ensembles that we are familiar with which is controlled by temperature. By the way, please feel free to stop me okay. So there are, of course, this idea of trying to address the statics and dynamics of this assembly is a very big question with lots of different aspects, and the particular thing that I would like to try and discuss is that this kind of granular assemblies or these granular solids within quotes under external force can result in jamming. And this force mediated solidification is what are often called jammed solids. And for example, this funneling effect, where if you put these sort of grains, and depending upon the size of grains and this angle, because of gravity, sometimes what you can get is this jammed structures which prevent this flow further. Okay, and more generally, if you take these assemblies and put them together and put some hard boundary and put forces on them, they start behaving like this solid features, in the sense that they have developed some kind of rigidity which amongst them, and I would like to try and talk about these kind of jammed solids, some aspects of this. Okay, and immediately what strikes us is that the mechanical properties of such jammed solids depends upon the non-trivial network of forces and torques that takes place between the different grains that are in contact with each other. For example, if you take this grain and sort of put some amount of force, then the transmission of that force throughout the rest of the grains takes a very non-trivial form, and that generates what is called the force network. And to understand the mechanical properties, we would need to understand properties of this network in addition to what individual grains are doing. Okay, and so this being the question, I'd like to spell out the answer that I'll try to impress you with, is that this mechanical response of jammed solids is best thought of as a dielectric response of a kind of tensor electromagnetism, and this is what the rest of the talk would be about. So, by the end of this talk, I'll try to explain that I'll try to show you that this kind of force network and various aspects of it are understood in the language of an electromagnetism, which is slightly different from the Jackson electromagnetism that we are used to, but it is very similar. I'll use very similar ideas and I'll point out the new features. Okay, good. So let's start with trying to understand what constitutes these mechanical properties in a bit more precise manner. Okay. So we have these jammed solids where we have these individual grains. If they're static, they are in force. Every grain is in a state of force balance and a torque balance, in the sense that if I go to one grain and ask it's in contact with other grains, and if I ask what are the contact forces, and that's this, so that must add up to 0, okay? And then similarly, if we ask for the torque acting on this grain, that must also add up to 0 at the single grain level. So this basically is controls the statics of the system. So then this lets us formulate this question about what is the distribution of these forces across this network of contact points of different grains, and this is the kind of thing that constitutes one signature of the mechanical response of these the jammed solids. Okay? And one indicator of this force network is what is called the force moment tensor, which is basically you go to each grain and you take this direct product of the distance from the center of the grain to the contact point, so here, and then you take the direct product with the force acting at that contact point, okay? And then if you sum over all the contacts for a particular grain, that gives you the force moment tensor. And the advantage of starting with this force moment tensor at the grain level is that the coarse graining of this object gives you the stress tensor, which we are sort of familiar with in context of elasticity and other things, and that's one way to characterize. So the distribution of the force moment tensor, or the coarse grained version of it, which is a stress tensor, that allows us to characterize this force network, and so let's try to do that. And starting with what happens at the grain level tensor, which is basically dividing it by the grain area and things like that. Okay? Good. So this is what I'll use, and the point is that this can be measured in experiments, and these are experiments of photoelastic, photosensitive discs in 2 dimensions, and what you do is that you put this disc together, and what you calculate are these distribution of forces and the stresses at the grain level using the equations that I just pointed out, and there are of course some details of how to go from the experimental data of this. What you measure is basically the refracted light and of these photosensitive grains, and then to convert it into forces, there are some subtleties which I can discuss after the talk, but I mean, people like Pinaki are real experts. So these are the kind of pictures that you get if you think about the XX component of this stress calculated in the way that I just pointed out, or the YY component, and you see that it is disordered, but it has some structure inbuilt into it. And the structure becomes very apparent when you think about calculating the stresses correlation functions in momentum space. And here you see this kind of plots for the XX, YY and XY components of stress, and it basically is suggesting, I'll come to the details of the structure towards the end again when we have developed the theory, but what it shows is that in spite of this random nature of this force network, or the packing of the grains, these stress correlations have some well-behaved structure in spite of the random granular assembly. Okay, so it's not that the stresses are arbitrarily distributed. So one of the aims would be try and calculate, develop a framework to calculate these stress correlations. Okay, so immediately, when we start thinking about doing calculations, we would try to understand what are the relevant equations, and so we would go back to the force balance and the torque balance equations to try and glean out the coarse-grained equations, which we can then try to use to find out how to calculate these correlations. And one immediate problem that we see is there are not enough equations to do this, and this is the problem of missing equations. The point is that this stress are matrices with d cross d dimension, the components, and the torque balance ensures that the stress tensor is symmetric, and so it reduces the d square to d into d plus 1 by 2 components. And then once we think about the force balance, we get these coarse-grained equations where the divergence of this the divergence of this stress is related to the body force, or this the force that acts on the center of the mass of these grains, like gravity, etc. We get these force balance equations. But you see that these are only d equations, one for each component. The component I is summed over, so there are d components. So there are not enough force balance equations to understand all the components of stress. Okay, so then we essentially need more equations to frame this problem more carefully, so that we can solve this and try to calculate what are the stress-stress correlations. And this is one of the central problems, as I'll try to point out, in these jammed solids that we need to try and address. Okay, so before we go there, let's take even a step back from jammed solids and try to think about the crystalline elasticity, the kind of things that we learn in undergrad coursework. And basically the point is that in that case, the missing equations are obtained via strain field. Okay, and this is as follows: that we think about the deformation of this solid, the crystalline solid, and think about the a displacement field out of which we form this symmetric derivative to define the strain field. And when defined in this way, it automatically solves this equation, which you can check. So this strain field, which characterizes the deformation of the solid under stress, along with this linear response which connects the stress and the strain via this proportionality constants, which are the elastic moduli, which are essentially material properties, give us enough set of equations to solve for the mechanical properties of the solid in the linear regime or the elastic regime. Okay, and this is one framework which we know and we most of us have used even to do experiments, undergrad experiments, and we are familiar with this. So this is how the problem of missing equations is generally solved in crystalline solids. Okay, so then the question is that why do we not do the same thing for jammed solids? Okay, and in principle it's always possible to do that in the sense that if you have enough resolution so that you can sort of zoom in onto every grain in experiments or in numerical calculations, then you can just track the positions of each grain and think about the displacement. You can always pick a reference configuration and do that. But I basically argue that a more satisfying and a natural way to explain this is in terms of electromagnetic theory, where you don't have to depend on such displacement fields, which I'll try to argue that they are much less physical in a jammed solid than in a crystalline system. And this is what I'll try to do next. Okay, so then the question to try and understand is that why should we use this new kind of ideas? And to do that, let's again go back to this crystalline solids and try to ask, how do we get to this strain fields, and why is this definition of strain field in the way that we did in the last slide makes sort of a natural way to progress in crystalline solids, but not in jammed solids. The idea is that in a crystalline solids, we have a spontaneous symmetry breaking, we have spontaneous translation symmetry breaking, and which results in a state where the ions are periodically arranged, something like this for a square lattice. And this basically provides a unique zero external stress reference state, and we can define displacements. It's natural to define displacements with respect to this thermalized state below the solid liquid transition temperature, and this is missing in granular solids. The analog of this is missing in granular solids. Okay, so the idea is that if you have this unique zero stress reference state, you can define a displacement field, like say for this ion, you displace it with respect to this equilibrium state of the crystal, and then you can sort of, starting with this displacement field, you can follow the recipe that we just outlined to get all the calculations done. The point is that there are no such unique zero stress reference state for the jammed solid. Okay, and so the displacement field is much less well defined here. Okay, and this is what I'll try to point out. So you can think about the final state of this jammed solid, and you can think about arriving at this stress state starting with a reference state like this crystal. Alternatively, you could start with this reference state 2, and it's equally valid, or you could start with something like as random, because there is no equilibrium thermalized state, and so all these are valid reference states from which you can try to calculate the displacement field and then try to define your strain field. Even weird, you can also choose the reference configuration somewhat locally, in the sense that for a part of the system you can think about the reference configuration to be of this kind, and for some other part of the system you can think about the reference configuration of this kind, and then there is no reason to think about favor one as opposed to the other. Okay, So hence this displacement field in some sense is not an observable when we calculate the configuration average stress correlation functions in jammed solids, and this aspect is somewhat different from that of crystalline solids or even amorphous solids in thermal equilibrium. Okay, so there is no reference state. And this aspect needs to be put in, and people, all of you are familiar with, who are familiar with gauge theories, realize that this is one feature of gauge theory where there are certain fields like the potentials which are strictly not observable within some framework, and this is the connection that I'd like to explore. Okay? So this brings me to the summary of the part 1 of the talk. And how am I doing with time? 25 minutes. Okay, good. So in crystalline solids, we have this broken symmetry thermal state, which provides a unique zero stress reference configuration, and then we use that as the natural starting point to define the displacement field and go on to do the elasticity theory based on that. But for jammed solids, this sort of breaks down, or there is no, let me say that there is no natural way to incorporate all these things on this side, and but there is still mechanical response which we would need to try and understand. And okay, so this being the problem, I'll try to point out some of the I'll try to point out one way of calculating these things, but before that, questions. Okay, then let me continue. So let me start with this flowchart, and this is the first point of departure from crystalline solids. So let's try to understand that in a bit more detail. Okay, so this when pointed out in this way, sounds weird, but it is not uncommon in condensed matter systems. And typically, the kind of things that, the kind of physics that I'm more familiar with, this is actually quite common and typically happens in what are called frustrated systems, where you have lots of competing interactions. And so let's go back and have a brief look as to what happens there, where you don't have these unique configurations, unlike the broken symmetry states. Okay? So that of course is like talk and a set of things by itself. So let me give you an example which also, yeah, please. Yeah.
Do this multiple times, I think do this multiple times and get some sort of an average.
Yes, so as I'll, so that's what I'll end with. So if you do that in in the language that I'll point out, that would be a gauge fixed version of doing the calculation, and that does. So if you do this correctly and if you sample this correctly, you would get the same result, but it would be independent of if someone else takes a different reference configuration and does the same calculations and same averaging. Okay? Yeah. Yeah.
So once your granular solid is young, how is it different from the amorphous solid?
Oh, so that does not have so this equilibrium configuration, whether it's periodic or aperiodic, in amorphous thermalized states is controlled by the temperature. Okay, just like the crystal. Okay, here there is no temperature which stabilizes. So if you take out the boundary stresses, the system just falls apart. Okay. Yeah. More questions? Okay then. So I was talking about this fact that sounds weird in this if you compare to crystalline elasticity, but it is not. It is actually quite common in other parts of. Okay, so other parts of physics where we have competing interactions, and instead of going through all the details and of that field, let's do an example. And the example is that of water or spin ice. The spin ice part has the connection. Rahul Siddharthan and B. Sriram Shastri worked on some of these aspects, I think when Rahul was a graduate student. Okay, so I'll give you this example, and what you will find that local energetic constraints in this kind of systems give rise to very low energy effective description, unlike the crystal and phonons that we are familiar with. Okay, so let's start with this idea of ice crystals. I think it's called the hexagonal phase of ice, where you have, these are the oxygen atoms, and these barely visible green things are hydrogen atoms. Sorry about that. So if I look at the central oxygen atom, there are 4 hydrogen atoms associated with it if I connect these oxygen-oxygen bonds, and out of them 2 are covalently bonded with the central atom at low energy or the ground state configuration. 2 of them are closely the covalently bonded, which is like this 2 hydrogen atoms which are close to the central atom. And the other 2 are hydrogen bonded, which is covalently bonded to the other oxygen atom, so they are closer to them, so they are farther from this central oxygen atom. Okay? So this is the low energy ground state configuration of ice, and the point is that at any time, if you sort of draw the displacement vectors from the midpoint of the oxygen-oxygen atom, there would be 2 of these displacement vectors pointing away from the central oxygen atom, and 2 of them pointing towards the central oxygen atom. So this is what is called the famous 2 in 2 out ice rule by Bernal and Fowler, discovered way back in 1930s. And if you count for a single oxygen the number of ways to do that, there are 6 ways. You just need 2 to be pointing out, 2 to be pointing in, and out of the 4 there are 4C2 or 6 ways. Okay? So now you start thinking about the pyrochlore lattice, which is made out of these, by drawing. So at the center of each pyrochlore lattice, there is this one oxygen sitting, and they form this pyrochlore lattice. If I draw it in this way, okay. So then you can ask that if I try to do this, and how many typical configurations that I get. And this number approximately turns out to be the scale exponentially with the number of oxygen atoms, and this was due to Pauling in 1950s, and it has its own a share of consequences for water, but this number is fairly easy to calculate. So think about this orange yellow the type of tetrahedra which encloses one oxygen atom. Okay, so see that this orange tetrahedra always connects with this grayish tetrahedra, so never with another orange tetrahedra as its nearest neighbor. So you can ask that, suppose you can make a rough estimate of the number of states by asking that, suppose I don't have this the gray tetrahedra, so this orange tetrahedra are sort of standing by themselves, so what are the number of possibilities? So then I can do this counting independently for this orange tetrahedra, and I have 6. So for n such oxygens, it would be 6 to the power n. But now I ask that, okay, for each of these configurations, if I bring back the gray tetrahedra, what is the probability that, given that these orange tetrahedra are in this ground state configuration, that the gray tetrahedras are also in the ground state configuration? And that you can calculate. It just turns out to be 6 by 16. 16 is the total number of states, and out of them 6 are allowed. So that then you take the product of those two, and that gives you this number. Okay, so that's a calculation that Pauling did in context of water ice, and the point is that it leads to macroscopic degeneracy in the ground state, and then there are no unique configuration like the crystalline state or this ferromagnet or whatever that we are familiar with from broken symmetry. Okay, so and then you can draw different configurations. I mean, these configurations, if you look in detail, you would find that so from this configuration these blue arrows are different, but if you go around each of these tetrahedra, you would find that 2 of them are pointing in and 2 of them are pointing out. These are 2 of these huge number of states. Okay, sorry. Okay, so so then what you can do is that if you try to understand the low energy theory of this system, you can define this displacement of hydrogen, these vectors from this midpoint of the oxygen-oxygen bond, as your degree of freedom, and sort of declare this as some kind of an emergent magnetic field or an electric field. And the reason is that this 2 in 2 out rule, now for this emergent magnetic field, nothing to do with this our electromagnetism at the 0th order, turns out to be a Gauss's law for this emergent magnetic field. Okay, and violating this Gauss's law would result in sort of excitations which you can think about in terms of magnetic monopoles. Again, nothing to do with the magnetic monopoles of the electromagnetism that's like allowing us to project project the slides, but the mathematical structure is same. And in fact, you can use this structure of emergent electromagnetism to calculate all the low energy properties, all the correlation functions of this low energy theory. So the point is that the low energy theory of the system, which does not have any unique configuration, gives rise to a low energy theory which is very different from, say, the theory of phonons or the theory of spin waves that comes from broken symmetry. And this theory doesn't look like this harmonic oscillator in terms of the phonon degrees of freedom, broken symmetry degrees of freedom, or more precisely the Goldstone modes, but in terms of a gauge theory, and that's very different from what we are used to, say, in Marvin-Ashcroft level physics. Good. So the point is that in this frustrated system, this local energetic constraints can lead to this Gauss's law type of structures, and gauge theories can emerge. Okay? In the simplest case, this gauge theory, you can just take this and add quantum fluctuations, you would get quantum electromagnetism, and you can just try to understand everything about these theories. Okay, good. So I'll take now a break and see if there are questions, but what I have pointed out is that if you don't have broken symmetry, you can get low energy theories which are very different from what like the theory of phonons or spin waves. Questions? I think so, but I can tell you. I think so, but you have to incorporate this some aspects of temperature. Okay. Yes, maybe. So the question is that whether that aspect of temperature is relevant or irrelevant is something that I cannot immediately tell you, but that's definitely a thought. Okay. That. More questions? Yes.
Since these systems are macroscopic, there's no concept of quantum in it, right? The emergent electromagnetism is classical.
So this part is classical, but I'll be very happy to tell you how to make it quantum. Actually, the spin versions of this, which are called spin-ice, one of the major things that people look for both experimentally and in theory is what is the quantum versions of this, and I can tell you after the talk how to generate the electric charge, the magnetic monopole, the photon, everything in this theory. You can go and ask what is the fine structure constant of this theory and things like that. So it is really an universe and QED by itself. It turns out to be a strongly coupled QED. Okay, more questions. The fine structure constant is 0.1, not 1 over 137. In what sense? So if I let me just try to go back. So yeah.
But the amount of this space is also important when you calculate.
So it turns out that that fluctuation is in a way gapped, because if you try to put in forces, you are fighting with Coulomb you are fighting with Coulomb potential, so that is no longer. So you can think about this displacement as rigid vectors, because if you try to sort of change the length, you have to pay the Coulomb energy cost. So it's a higher energy excitation. Yeah. Right.
May not be valid here, and maybe there are some other constraints. How to translate that language?
Oh, sorry, maybe I went over this. So for the particular aspect that I am considering, this ice structure just gives a background, but what I am interested in is this the displacement, the proton disorder. okay, the hydrogen, the position of the hydrogen, okay. So for that there is no reference configuration is what I am trying to point out, okay. So the ice provides a background for this proton disorder, but if I think about these protons, okay, they can randomly be on this bond either away from the oxygen or towards the oxygen, okay. So as far as the proton displacements are concerned on this network, so what I'll do is that so here the network is regular because it sits on a lattice, but the displacement vectors are random, okay. Yeah, so the network is regular, so the oxygen positions are regular, the hydrogen positions are disordered, okay. So what you would see in the jam solid, it's like this hydrogen problem, not the oxygen problem, okay. So oxygens I have solved, it has gone into crystal, so it has no low energy behavior at the 0th order, okay. Yeah. So it's a frozen crystalline background, yeah.
Which
Yeah.
is classical system, but you can have a case where the monopoles are all condensed, whereas
Yeah, so all those things.
What are the analogs of this physically?
So it's hard to have the monopoles condensed in the water version of the problem, but for the spin version of the problem, that corresponds to some magnetically ordered states. So you could understand them as a confinement transition of things. Again, the entire thing about QED or things like that with the electric and magnetic charges applies for this system. Okay. More questions?
So, probably I missed it. Please, individual geometry of your individual granular solids do not matter.
Huh?
Individual granules, the geometry of these granules, you are assuming them to be spherical?
I'll assume them to be spherical. So I think that if you, I'll assume them to be spherical. If you, why don't you ask this question at the end of the talk? And the short answer is that I'll show you that all that changes if you change the spherical symmetry in the linear regime is the symmetry of the dielectric constant. Okay? If you have spherical the granules, the dielectric constant also reflects that symmetry. If you take, say, rods or something and you think about sort of similar jammed structures and their mechanical responses, the elastic constants would reflect that symmetry. Okay.
Probably my other two questions are also for the end, but let me ask straight away. I vaguely remember even though, like you said in the beginning, there is no notion of temperature, there is some kind of notion of effective temperature that comes out sometime in terms of compact-activity.
Question for Pinaki.
So that has no effect on the aspect you are discussing?
Yeah, no.
Okay. If I want to ask a very simple question like, when does my, if I want to sell my salt as, the salt which flows, like in the advertisements, do I already have an understanding in terms of what you have all discussed, or would I have some understanding of how
So
to
I will
design?
provide the framework. The dynamics question is left for all of us to solve. I'll point out some aspects of dynamics, but not the flow aspect. I don't know how to address that. So, okay. Yeah. So that's related to the unjamming type of things, which, yeah. More questions? Yeah. There is.
So here you have. So here you have emergent abelian gauge theory. So
Yeah.
there must be, or are there systems with emergent non-abelian gauge theories and with strongly coupled systems, and like, because even they are not even very well understood in high energy theory.
Right,
So-
right.
And here you
again,
have yes,
people
and
like Anton.
here you have experiments as well that you can just perform and see things.
Sometimes, yeah. you can get non-abelian theories, even weirder things that I'll talk about. Okay.
Okay. So there are systems with emergent non-abelian gauge theories.
Yeah.
Okay.
Okay. I'll just move on. I think. Okay. So then let me try to flesh out the idea and then go into the detail. So the idea is that this force balance, you can now think about this as a Gauss's law, and this is in fact a Gauss's law, just like we found out in this case where the displacements were promoted to this effective emergent magnetic fields, but here the Gauss's law is much more involved, not really involved, but it's slightly different from what we are used to, is where the charge, which is the force sitting on the right hand side, is a vector, and this new kind of Gauss's law allows vector electric charges or magnetic charges, it really doesn't matter, and the electric field, the analog, the stress is the analog of symmetric electric field, symmetric tensor electric field. So the earlier example that I told you about, where the low energy degrees of freedom, this displacement turned out to they were vectors, and they turned out to be gave rise to this usual vector electromagnetism, but here we are dealing with tensors. We can do the same kind of coarse graining, and we arrive at this force balance condition where this divergence is that of the stress field, and which is a symmetric tensor. So if we want to try and promote this to electromagnetism, we cannot do this with our usual electromagnetism, but we have to deal with a symmetric tensor electric field and the charges which are no longer scalar but vector charges. Okay, and note that just like this ice problem, it trying to talk about this local force balance does not need any unique reference state to start from. Okay, so this is what I'll try to push and try to point out in some detail, and then I'll this is the thing that I would like to finish with is to show that this explains the correlation functions, the stress correlation functions and the stress response in jammed granular solids, and with some modification that I have to talk about a dielectric of this material, and which comes from the fact that you cannot have the zero stress assemblies which are well defined. Okay, so but let me just quickly give you a one slide introduction to this new kind of electromagnetism, which is a well defined theory, and we can discuss all aspects of it after the talk. You can try to write down Maxwell's equation for this symmetric gauge fields, and like the electric and the magnetic Gauss's laws, which are of this form, and then the Faraday and the Ampere laws, which are basically so this looks ugly, but what these really are basically usually these are this curl of E and curl of B, but here you have to take curl with respect to the first index and curl with respect to the second index, and that's all this is. Okay, so I've also put in the magnetic charges and the currents, but you can people know how to do electromagnetism of these things, and you can form you can ask all the questions that are there in Jackson and solve them for this tensor electromagnetism, which goes under the name of vector charge theory, because the charges are vectors. Okay, now the most important aspect of this theory is if you think about the conserved quantities in our usual electromagnetism, the total charge is conserved. Here what is also conserved is this cross dipole moment. So this is the first moment of the charge. There is this antisymmetric part, so there is this cross dipole moment, but this is the first moment, so it's in that sense it's a dipole. So both these things are conserved, so not only the charge but also the dipole. Okay, And the second conservation is basically, this means that you cannot move even if you have isolated charges. So suppose you have two charges of positive and not really positive, these are vector charges. So you have a vector charge here and a vector charge there, maybe oppositely aligned, so that the total charge is 0. Okay, so then the dipole moment, you can define a dipole moment using this rho cross r, and you just cannot move one charge freely because that would change this dipole moment. Okay, so unlike our electromagnetism, the local charges are not allowed to move. Okay, so this places a lot of constraints, and this is the reason why these kind of theories have been looked at, and some of you may know in context of weird phases which are called fractons. Okay, which are basically charges of this object which are not allowed to move. Okay, so the point is that the jammed solids, the mechanical response of jammed solids is a dielectrics of this vector charge theory, and the reason why it's a dielectric is basically that the jammed solids exist only under external boundary force, and when I have such boundary forces, that in this language can be thought of as external charges, which gives rise to external electric fields under which this system is in, and that basically leads to this force network, which are these contact forces, which then can be looked up as internal bound charges, bound because they are sort of stuck to the contact of these grains. Okay, so you have put this external force, or in this language charge, and you get a response through the force network comprised of this contact forces, which are like the internal bound charges, and that's why it should be interpreted as a dielectric rather than a free theory in vacuum. Okay, and let's try to understand the structure in the electrostatic limit, where you can compare it with experiments as well as numerical calculations. And so, like, can I have like 10 minutes? Okay, so in the next 10 minutes I'll try to point out that how this works, and you can look up at these two things, two papers, to see how to derive this structure, how to actually control, in a controlled way, do this mapping from the equations of motion or the Newton's laws for the granular solids to this set of Maxwell's equations. Yeah. Huh?
Those things are bound. You said they are bound. They cannot independently.
Yeah, so
move.
they're bound because they're sort of, I mean, so think about the force acting on that contact. It's sort of bound to that contact, right? So as long as you don't change the network structure, okay, the force is sort of has to be at the contact of those grains. Okay, so in that sense, trying to sort of use the analogy of electromagnetism, those charges are not free to move.
In that sense, what is the range of this? Like, how does it affect other bound ones? Is
Yeah,
it
I'll do the, that's the dielectric theory, right? Okay, good. More questions? Yeah.
Could you explain, sir, how this dipole is different from vector charge?
Huh?
How dipole is different from vector charge? A single dipole, when we use in electromagnetic theory,
Yeah.
how it is different from vector charge you are using?
Yeah,
here?
so the easiest way to think about is, as I said, look at the continuity equations for the dipole. The dipole current is not conserved in usual electromagnetism. Here it's conserved. There is a continuity equation I could write down for the dipole current. Okay? Yes.
You're talking about that it can also flow. The granular solid can also flow. So some of this can use the full dynamical equations at some point.
I'll point out one aspect. The general answer is no, because it depends upon boundary conditions, etc., etc. But I'll point out one aspect.
So I mean, this continuity equations for the charges of these two dipole squares, is it will be valid in this more general scenario, or?
So I'll give you an even simpler example. This is Maxwell's equation, so it has a wave solution. Okay, I'll briefly talk about that wave solution. Okay, yes. Okay, so let's look at the electrostatic limit and see if we are going in the right direction and try to make contacts with experiments and numerical calculations, and then try to understand all these very important aspects. So how do I develop this dielectric theory? And let's forget about the granular solids. I have Maxwell's equation, I have these charges, I go back to Jackson or any electromagnetism book, I rederive the theory of dielectric for this system, and here it's a straightforward extension that I can think about the total charge density as the sum of the external charge. All these uniqueness type of theorems, etc., are all valid for this theory. Okay, so I write it down for as a sum of the external charge or the free charges and the bound charges, and the bound charge I can connect it with divergence of a electric polarization, which now turns out to be tensor. Okay, I'll connect it to the granular case in a moment, but you can do all this formal manipulation and you can define an electric displacement field, which is again a tensor, which now solves the Gauss's law in this form, where on the right hand side I have only the free charge density, all the things that we learn in electromagnetism. Okay. So the mapping turns out to be actually this, that the electric displacement field is what maps to the average stress field. Okay, not the electric field, the electric displacement field, whereas the actual electric field maps to the grain level stress tensor. Okay, so this is exactly like if you keep track of all the charges, you get the total electric field, but if you only keep track of charges or the here the forces that you put on from outside, you get the electric displacement. Okay, and the electric dipole moment is the contact stress. You don't sum over all the contacts, but you take one contact and calculate this direct product, and basically that's what this electric dipole moment is. And you can sort of have to take my word for this, and all these calculations you would find in gory detail in this two papers. Okay, so we would now with this identification of the in the electrostatic limit, we would now like to calculate the stress correlations and responses and try to understand this. Okay, good. So let's try to do that, particularly in the linear response regime. Let's try to see if there is such a linear response regime. A priori, we don't know that such a regime exists or not, but we have to try and see if such a regime exists. So you do again all the things, but with more indices. Here you define this dielectric response coefficients, which are now 4 index objects, and note that these are all properties of the network, and primarily, and not the properties of the materials themselves. It might depend upon the aspect ratio of these grains, but not in primarily on the material with which you make these grains. Okay, so in particular, this relation is like the stress-strain relation, but we must remember that this is basically a dielectric response, whereas this is an elastic response. So that's the connection. Okay, and in fact, this is the reason why we choose to call this dielectric response as sort of emergent elasticity, because it's sort of similar linear relations in the elastic regime. Okay? So then the question is, does this elastic regime exist? Okay? And we can test this against numerics and experiments, and the two tests that I'll talk about are the stress correlations and response to point force. Okay? And the low energy symmetry allowed theory in terms of this electromagnetism, this electrostatic limit, is this subject to this constraints, and then with this theory, which is a Gaussian theory, in the linear response regime, I can calculate the 2-point correlator or the response, which is I put a test force and I calculate the change in this displacement field. So these are the two things that I'll show and compare it with experiments and numerical calculations. Okay? Good. Questions? Okay, so here is the test in 2D. Okay, so let me try to point out. So this is the theoretical prediction of how this went fast. So this is the so I'll start with the stress correlation, which is basically this object. Okay, in the Fourier space. Okay, so this is what the theory predicts. Okay, for the CXXXX correlation function in the Q space, as you see, and this is the angular cut. Okay, so then what you see in numerics and experiments are sort of encouraging things, but note that the numerics and the experiments are on finite systems and they have a UV cutoff, so that's what is showing up. So if you want to really compare this, you should compare this with a zoomed in version of this the theory of this numerical calculations and experiments, but you see the general symmetry pattern. Okay, and these are more detailed analysis of the XY correlations and the angular pattern. So in this the black lines are these, and the red points are coming from numerics or experiments. And all you need to do, there is also four other of them. All you need to do is to say take XXXX and fit this for this curve overall constant or normalize this overall scale, and that's it. You don't use any other fitting function, any other fitting parameters. You just fit the overall scale for one, and everything gets normalized. Okay. Okay. So the immediate feature that was known in the community, and this theory immediately predicts, are these pinch point structures, these singularities that at near q equal to 0, which is a direct consequence of this low energy gauge theory, the structure of the theory that I wrote down. Okay, and you can look at all these features for different components, and you find that this just generally follows from the structure of the theory that we constructed. Okay, you can make more elaborate comparisons by taking a fixed q and looking at the angular distributions, and you have to take my word for it. There are, beyond this one single parameter normalization, there are no other parameters that we have tinkered to get this fits. Okay, so that sounds really encouraging. So one can go and try to check this with all other correlation functions. These are comparisons with numerics, and we have all these plots in our latest longer edition, and this works out to an encouraging extent. Okay, so moving on to 3D, now there are 21 of them, and there's only 2 symmetry allowed free parameters if you take circular or spherical grains. Okay, so And this is for the YY component, and this is the numerics. There are some problems with sampling near the poles, but this is a theory, and again you see that this comparison is the symmetries work out pretty well. Okay, so I would leave you with trying to find out all these comparisons, and you would see that for all the rest 20 of them it works out fairly well, and you can have a look at this at your leisure in one of the papers. But let me just quickly point out this other signature, the response to a test force in 2D, which we are also able to calculate using this Gaussian theory, which is fairly straightforward. So you put in an additional force downward on this set of grains, and you put in the same force now distributed over this line of grains in the opposite direction, so that it remains in mechanical equilibrium. And then you ask what is the difference of the stresses in presence and absence of this test force, and you can calculate and you can try to convince yourself that this works out. Again, this does not require any more parameter than the scale, so these are all completely fixed by the single scale that you have in the theory for 2D, and two scales, two parameters that you have in 3D. Okay? Yeah, again these are like the things, and one can go on, and basically the point is that this displacement not being an observable within quotes, what results is emergent electrodynamics of this tensor kind, and whose dielectric, linear dielectric property explains the elastic behavior in these granular solids. So coming to these questions about dynamics, I'll just point out that you can try to understand all these behaviors in its full glory, all these almost in its full glory, starting from this Newton's law, now including the momentum density as here, and what you would find is that these are much less understood features of the theory, because it's harder to do experiments as well as the numerics. So to compare with the theoretical ideas, but what seems to be happening is that the momentum density acts as a magnetic charge, and the magnetic field is then is sourced by this momentum density and is related to the dynamics of the particles, which sort of lead to breaking of the network. So when the particle starts moving, it leads to the breakage of the network, and that's what the magnetic sector seems to be capturing, unlike the electric sector. So at present we cannot derive the Ampere's law, but we just from this Newton's equation and what we know about all the constraint equations, but we just go ahead and postulate it, and then the question is that we can ask, if I postulate that law, what are the consequences? Okay, and one important consequence is this emergent light, the wave solutions of Maxwell's equation. And now, since roughly there are two derivatives of space on one side and one derivative of time, the light has this dispersion. It's not linearly dispersing but quadratically dispersing, and that gives rise to a non-Debye density of states. And one can go and ask that, is this non-Debye density of state seen anywhere in the low energy excitations? And that seems to be an open question, and right now it appears to us, and particularly to me, that this density of state depends upon the kind of experiment on numerical things that you calculate, and particularly if you calculate some of these density of state using sound velocity probes, it seems that you see something similar to this, but this clearly requires more thought and calculations. Okay, so with that, I'll stop. What I have tried to point out is that granular assemblies can behave as solids under external stresses, and since there are these no unique zero stress reference states, the displacement field is not an observable in the sense of crystalline solids, and this shapes up the structure of the low energy theory, which basically starts by taking in the force and the torque balance conditions to formulate a Gauss's law in terms of a symmetric Yuan tensor gauge theory, and the stress field are quantitatively characterized by this theory in the elastic regime, so to say, which we have explored in detail. This of course leaves out various very important questions that the community has been thinking, and the most immediate question is that what gives when this linear response breaks down? So we have nonlinear response, so this writing as P as proportional to E does not work. And what immediately happens is that you start getting quadrupolar singularities in the field, and remember the charge and the monopole and the dipole are conserved, so the lowest multipole that's allowed to fluctuate locally is the quadrupole. So this theory actually allows for these quadrupolar singularities to form locally, and this is one nice aspect. And these various aspects of dynamics, including the low energy density of state of this emergent light, and needs to be probed. But coming to this point that you could use the displacement, and how does this displacement based methods connect to what we have tried to point out? And one way is that this displacement based methods where we choose a reference configuration is like gauge fixing the theory and doing those calculations. So these are things that I won't even go into, the unjamming transitions and the crystallization transitions, how does this gauge theory take shape, but I'm happy to talk about after this. So with that, I'll stop, and thank you for your attention. Sorry for going over time.
Thanks, Subhro, for a very nice talk.
The floor is now open for questions. Yeah, Shantan.
So, suppose you are doing electrodynamics in your formalism. So suppose you calculate the Poynting vector. So, is it possible to now see how, if you give a force at some point, how will the long time dynamics, or how this
So
whole.
you're asking about the Lorentz force equation.
Yeah.
How does it look?
Will it tell us about the long term, like the structure that forms at a very long time?
Yes. So even before that, full Lorentz equation is complicated, but Lorentz force law. But one outcome of this you can ask is that what is the how do you generate electric currents? Okay, or the Ohm's law version of this. Those we think are related to particle flows and things like that. And particularly the magnetic current is related to that. We can, so some aspects you know, but not really the entire thing.
So you've said multiple times that the displacement field is not an observable, and that's the reason of the gauge freedom in the system, right? So, but it doesn't seem right to make it or call it equivalent to the vector field, the A mu's. So because of the electric and magnetic fields being the tensor, so what exactly is the gauge
So it is
structure?
actually an analog. Do I have a chalk somewhere? So it is an. We just have dusters here. Okay, so it is basically so since we are talking about electrostatics, we should really compare it with the scalar potential. Okay, so since the electric fields are tensors, the scalar potential is now a vector. Okay, so one can write down similar equations as in terms of how the electric field can be written in terms of the scalar potential. Here now the vector potential, it turns out to be like a symmetric combination of del I phi j and del j phi plus del j phi I. Okay.
So the displacement field is in some way related or equivalent to the scalar potential.
Yeah.
All right.
Okay, but now it's a vector. Okay. Because of this.
Wait for a few more questions. Do you want to say anything about this crystallization? Maybe there's something interesting for people to.
Okay, so at the risk of saying something wrong, so it turns out that this crystallization transition looks.
So maybe just to basically what he's discussing is you go from an amorphous state to a crystal. So that transition, how would it show up in this theoretical framework?
Yeah, so if I try to drive this amorphous solid, this athermal solid to something like glass or the crystal, okay, something which has thermal equilibrium state, which is a zero stress reference state. So how should I think about it in this formalism? Okay, at the risk of saying something wrong, it looks awfully similar to a Higgs transition of this, where some of these aspects of non-observables become observables, and you can actually build up a phenomenological theory in the same sense as Pippard's theory of superconductors, etc. And okay, so that's all I have to say. But I don't know how to test this. We don't know how to test this in a very concrete way with numerics, and so more tests are required. Okay, yeah, if you say so.
Thanks, Subhro, for this very interesting talk.
Okay, thank you.